So, good morning everyone and welcome back to this NPTEL lecture series on cycloaddition reactions. So, in the last lecture we talked about Diels-Alder reaction and also on the stereochemical outcome of 4+2 cycloaddition reaction. So, what we will do now, so in this lecture also we will continue our discussion on the stereochemical outcome of Diels-Alder reaction and then move to regiochemical outcome of our 4+2 cycloaddition reaction. So, when we talked about stereochemical outcome and we also mentioned and discussed about the approach of dienophile to the diene from the bottom phase or from the top phase. So, for example, if you look at the Diels-Alder reaction between butadiene and benzoquinone. So, if benzoquinone approaches butadiene from the bottom phase, then the transition state will look like this. So, you can see here, so if this is the transition state and that in principle should give this product, and this can be written, if you rotate it like this, then you can see this is the product and this is the endo product. Okay. So, you can see that the double bond which is under the diene, okay, and this carbonyl group, okay, they are under the diene. Okay, that is why this is endo product. Same thing, if you look at the Diels-Alder reaction where the dienophile, the benzoquinone is coming away, it is not under the diene, it is away from the diene, then that will lead to exo product. So, if you write the transition state like this, you can see here now the whole electron withdrawing group carbonyl on both sides, it is away from the diene and it is not below the diene. So, this transition state will lead to your product like this. Now, if you see this hydrogen, these two hydrogens are alpha, whereas here you can see these two hydrogens, when you rotate like this, that becomes beta. So, what you get is this product and this is nothing but exo. So, what is very important is how you draw this transition state. First, you have to bring the diene and you have to bring the dienophile under this. Okay. When you bring the dienophile under this, the substituent on the double bond should be below the diene. Okay. Then only you will get the endo product. Or if you write like this, you bring the dienophile and the substituent, if it is away from the diene, that will lead to the exo product. Okay, so, this is very important. Once you practice this, then you can write any Diels-Alder reaction product by writing this type of transition state. Then from butadiene, suppose if you connect the butadiene, so this is butadiene and then if you connect it by a methylene group, then that diene is cyclopentadiene. So, earlier if you see this butadiene, these two hydrogens are inside substituent, isn't it? Here the inside substituent is CH2. So, now if this cyclopentadiene undergoes 4+2 cycloaddition with benzoquinone, then you can draw a transition state like this. Okay. So, when this dienophile approaches cyclopentadiene from the bottom phase, then automatically as per the transition state, here if you look at the butadiene, these two hydrogens will go up. Now, in cyclopentadiene, this methylene will go up. Okay. When this comes from bottom, automatically it pushes the methylene to beta. So, that should lead to this product. Now, again like butadiene, if you see these two hydrogens will be beta. The hydrogens coming from the benzoquinone, now it will be beta, and if you rotate it like this and you get this product. So, we also will use this intermediate when we talk about 2+2 cycloaddition reaction, how these two alkenes which are very close can undergo an intramolecular 2+2 cycloaddition to form very interesting basket-like compound. Okay. The same thing suppose if you have to draw exotransition state, so then what you should do, like the butadiene case, you also write this benzoquinone where you can see the carbonyl group away from the diene. It is not under the diene, it is away from the diene, and that should lead to this product. And again you can see here these two hydrogens are alpha. If you rotate it like this, then these two hydrogens will come alpha, and here this is the hydrogen, and you can see this is the exo product. So using these two examples, you should be able to extend this for any Diels-Hall reaction, how to write endotransition state and how to write exotransition state. And these two examples, what we have done or what we have discussed is use the bottom phase approach of the dienophile. Okay. And in literature, sometimes they write products where the dienophile approaches the diene from the top phase. Okay. Then you should not get confused. It is just nothing but relative stereochemistry. It can approach from the top phase as well as from the bottom phase. Okay. Only if you have a chiral center or external chiral environment, then you have to use only one. Otherwise, you can write the product where the dienophile can approach from the top phase or from the bottom phase. So now I will give same thing where the dienophile approaches the diene from the top phase. The benzoquinone, as you can see here, approaches the diene, that is butadiene, from the top phase. So here you can see again these carbonyl groups. Okay, they are in the case of top phase approach, if the diene is like this and with the dienophile is above, and the carbonyl groups, that is the electron withdrawing substituents which are attached to the double bond, should be above the plane of the diene. Here you can see here this carbonyl and this carbonyl are away from the diene. So this is an exercise. Now you can write the structure arising out of these two transition states. Likewise, you can also extend this to cyclopentadiene, where you can see the benzoquinone approaches the cyclopentadiene from the top phase, and here it is a exo transition state where again the benzoquinone approaches the cyclopentadiene from the top phase. In literature, many times you will see cyclopentadiene being used as diene. Even here, I don't know, we are given example, but the cyclopentadiene normally it exists as cyclopentadiene dimer. So this is the dimer. When you order a cyclopentadiene, you get only cyclopentadiene dimer. So what you have to do is you have to do the cracking. So the cracking, if you heat it and it undergoes a retro 4+2, you can see this will undergo a retro 4+2 to give cyclopentadiene. For any cyclopentadiene based Diels-Hall reaction or any other reaction, you have to start with cyclopentadiene dimer and then heat it, and that will undergo cracking or retro 4+2 to give 2 molecules of cyclopentadiene that can be used in subsequently. Okay. So far what we discussed was various stereochemical outcome of 4+2 cycloaddition reaction. As I said, in diene you have the terminal carbon atoms, and in the dienophile you have 2 carbon atoms. So overall there is a possibility of generating 4 new stereocenters, and they are interrelated, and the stereochemistry in diene as well as dienophile, they are retained in the Diels-Hall reaction because the whole process is a concerted process. Now the next major thing in Diels-Hall reaction is the regiochemical outcome of 4+2 cycloaddition reaction, and how does it happen, and which factor controls the regiochemistry of the Diels-Hall reaction. So it is believed and it is proved that Diels-Hall reaction always proceeds with very high degree of regioselectivity. The reason is, so In the case of Diels-Alder reaction, particularly the normal Diels-Alder reaction where you have diene with electron donating substituent and dienophile with electron deficient substituent, the HOMO of diene is involved and LUMO of dienophile is involved. Okay. So, but if the electron withdrawing group is powerful or more electron withdrawing in nature, and likewise in the case of diene, the electron donating group which is attached to the diene is strongly electron donating, then the final outcome where the regioselectivity will be very, very high. Okay. So, the reason or origin of this regioselectivity is based on the electron density of the terminal carbon atoms of the diene and also the size of the lobes. So, theoretical calculation says the size of lobes, or in other words orbital coefficient of reactant orbitals responsible for the regiochemical outcome of 4+2 cycloaddition reaction. So, when you have a diene, what are the possibilities? See, we can write, see for example, so this is the diene, okay. I write 4 different dienes, okay. All are same. Now I put substituent here at carbon number 1, okay, and I also put substituent here. In the next 2 I put substituent here and put substituent here. Now if you look at these two are same. Likewise, if you look at these two are same. So when you have diene, there are 2 possibilities if you have mono substitution. Okay, it is either 1 position or 2 position. Okay, so these are the 2 possibilities when you have a diene with only 1 substituent. So what will happen if you take these dienes and then do a Diels-Alder reaction with dienophiles? Okay. If you take 1 substituted diene, okay, then in principle there are 2 possibilities. One possibility is the substituent on the diene and the substituent on the dienophile. Now they are 1-2 related in the product. This is one possibility. The second possibility is, you can see here, the substituent on the diene and dienophile, they are 1-3 related. Between these two, this is the major product. That is 1-2 is the major product, or sometimes 1-2 is the sole product. So how does it happen? How do you give explanation? Again, you have to use the endo rule first. Second, you have to use the electron density, okay, or the orbital coefficient. Okay. Likewise, if you have 2 substituent, then in the product you can see the substituent on the dienophile and the substituent on the diene can occupy 1-3 position, or they are related 1-3 in the product. Another possibility is they are 1-4 in the final product. Between these two, 1-4 product is the major one. Okay. So why 1-2 is major and 1-4 is major in the case of 2 substituted diene? So if you take 1 substituted diene, say for example, simple example, you take 1-methoxy diene now, or any alkyl group attached at carbon number 1. In simple electronic arrow movement, you will see that electron density is more at carbon number 4. This is 1, this is 2, this is 3 and this is 4. So at C4 electron density is more, and if this undergoes Diels-Alder reaction with an electron deficient dienophile. So now what happens? EW. Okay. So for example, if this is ester, okay. So now because of the electron withdrawing group present at this carbon, now the delta positive charge will be more at carbon number 2. This is 1, this is 2. So, what will happen when you do the Diels-Alder reaction? Then the Diels-Alder reaction will happen in such a way that it will undergo the Diels-Alder reaction between carbon number okay. So, this is what will happen. Then it is not exactly this way because of the lone pair of electron, but because of the electron density. So, this is how the reaction will take place. That will lead to your 1,2 disubstituted cycloaddition. Okay. Same way, now you can ask how the stereochemical outcome also. So, the regiochemical outcome is because of the electron density, and for the stereochemical outcome already we discussed about the exo-endo concept, and you can bring in the exo-endo concept here. So, that will answer how you can draw. So, now if this is the transient state, that will lead to this product. Now, these two hydrogens are cis and then beta. So, this can be drawn like this. And these two hydrogens are cis and beta, or in other words, the alkyl group and the electron withdrawing group are alpha. Okay. So, likewise, if you see the two substituted alkene, okay, and when you have two substituted alkene, as I already mentioned, the 1,4 product is the major product and not 1,3. Though you may get a little bit of 1,3, but the predominant product is 1,4. Again, the same, the electron density could be utilized to explain, though there are other ways to explain, but this is easy for you to understand. So, now if you use the lone pair, the electron density is higher at carbon number 1, and likewise you will see here the electron density is low at carbon number 2 of your dienophile. So, automatically you will see that the new bond will be formed between carbon number 1 and carbon number 2, and that should lead to your 1,4 product. In both the cases, what we have done is we assume that the dienophile comes from the bottom phase of the diene, and the regiochemistry is explained by the electron density. Okay? And in both the cases, if you see, we have done with only one electron donating group attached to the diene. So, this simple example, as I said, we start with 1-methoxy-butadiene and methyl acrylate. So, that should give this product. How about having two electron donating groups attached to the diene? So, what will happen? Will it increase the reactivity? Will it increase the selectivity both in terms of regiochemistry and stereochemistry? Yes. So, Danishefsky prepared this very famous diene. If you look at this diene, you know that at carbon number 1 you have electron donating methoxy group, and carbon number 3 you have electron donating OTMS group. Okay. So, now if you have a closer look at this diene, it has a combination of, I will write it here to make it more clear, and in this case, if you look at these two dienes, the methoxy is at carbon number 1 and then OTMS is carbon number 2. So, if you combine these two, so you have methoxy at carbon number 1 and then OTMS at carbon number 3. So, it has advantages of both one substituted and two substituted diene. So, that means it will be more useful and the regiochemical outcome, the stereochemical outcome will be much higher because of these two electron donating substituents at the right carbon. So, what will happen? That will give you this product. Again, the stereochemistry, as I have already discussed, it is easy to write the correct stereochemistry, and if you look at this, so the new substituent, that is ester coming from the dienophile, is related to methoxy in a fashion 1,2, and same thing now the ester is related to OTMS in 1,4 fashion. As we have seen, 1,2 and 1,4 are the most preferred, and in this case now you can see a combination of 1,2 and 1,4. So, that is why this is the most preferred, and you in fact you get only this product. What is the other product one can expect and why it cannot form? The other product you can expect is this. Okay. So, now if you look at this, with respect to OMe, the ester is 1,3 related. Likewise, with OTMS also the relationship is 1,3. So, as we have already discussed, 1,3 is not really a good option. So, either it should be 1,2 or 1,4. So, that is why this product will not form, as this is a combination of 1,2 and 1,4. This is the sole product formed in the Diels-Hall reaction when you use Danishefsky diene, and because it has two electron donating groups, this reaction also works very well, and then the selectivity is extremely high. And second thing is, after doing this Diels-Hall reaction, one can treat with acid to get a cyclohexenone. So, how does it happen? If you treat with dilute acid, then this gets hydrolyzed. So, basically what happens? You take this OMe, then enol TMS. So, now the protonation takes place here when you treat with acid. So, now the enol TMS ether removes the methanol and use this arrow. So, basically you get now the hydrolysis of this will give you ketone. So, this is a very interesting method to make 4 substituted cyclohexenone. That too, the substituent at carbon number 4 is electron withdrawing group. So, that is why this particular method of using Danishefsky diene in Diels-Hall reaction really was useful in synthesis of many natural products where you need an electron withdrawing group at carbon number 4. Later, Rawal from University of Chicago modified this and made a slightly better diene, where if you look at this diene, where instead of OMe what you have is a diethyl amino group. Okay, OMe is replaced by better electron donating group, that is diethylamine. And in this case, if you see, in the case of Danishefsky's diene, you have OMe at carbon number 1 and OTMS at carbon number 2. So, what Rawal did is he replaced it by NMe2, it is a better donating group, and also instead of OTMS, TMS is slightly labile. So, instead of that, the more stable OTBS he has used. So, this more stable OTBS and the more electron donating NMe2 made this as a much better diene. Later he also changed from NME2 to a pyrrolidal group. Okay. So these three dienes he has nicely exploited in Diels-Hall reaction and made a few good natural products. See, for example, if you take Weresch-Rawal's diene and then treat with this unsaturated aldehyde. So this is a dienophile and this is commercially available. So first you should draw a proper transient state. So this is NME2 and this is OTBS. So now you have the diene. So what happens? So the dienophile comes below the diene. The dienophile comes below the diene, whereas the aldehyde is just below the diene. So now you can draw or put the dot, and if this is what is the transient state, which is supposed to be because the dienophile properly approaches from the bottom phase, that should give so now you look at this aldehyde will go alpha. This aldehyde and this hydrogen, they are cis to each other. This aldehyde and this hydrogen are cis to each other. So this also will be alpha. Okay. So this is what you will get. So if you do the Diels-Hall reaction between Rawal's diene and this aldehyde, this is what you get. Now again, like Danishefsky diene, if you treat with acid, it will undergo hydrolysis followed by formation of alpha beta unsaturated ketone. So now you can see this very interesting complex bicyclic compound. One can easily use this method to elaborate into much complex natural products, further exploiting this functional group, a carbonyl group, a double bond and a disubstituted alkene. So you have, in principle, there are 4 functional groups which we can utilize very nicely for further extrapolation. But overall, how many steps? It is done in one step, that is Diels-Hall reaction followed by one part hydrolysis, directly giving this complex starting material or intermediate to make many complex natural products. Okay, so that's the beauty of the Diels-Hall reaction. So you can extend this with Danishefsky diene instead of alpha beta ansoge ester, which we have discussed. Now if you use methacrylene, so again you can use the same like transient state. So this is how it will form, and if this happens, so the aldehyde will go inside and methyl will be outside, and later upon hydrolysis, so you will get this compound. Okay, so that is nothing but your cyclohexenone, and you can see the methyl group beta and aldehyde alpha. Okay, so it is very easy to prepare a 4 substituted cyclohexenone having the electron withdrawing group at carbon number 4. So that's the beauty of this Danishefsky diene as well as Rawal's diene. So now if you repeat the same with Rawal's diene and methyl acrylate, so now you can see you will get this compound, and if you hydrolyze, or one can also reduce the ester. If you hydrolyze, you will get the alpha beta unsaturated ketone, but if you reduce with LAH, the ester group will be reduced to get the primary alcohol, and followed by HF treatment. HF treatment will remove the TBS, so that will lead to enol, and then followed by formation of cyclohexenone. So what Rawal has cleverly done is, earlier we were thinking that this method is useful for introducing an electron withdrawing group at carbon number 4 of cyclohexenone, but by doing LH reduction, now you can see you have the electron donating group, that is CH2, which is an electron donating group. So, electron donating group also can be at carbon number 4. Thank you.